Okay, just wanna basically talk about Go's array and slices, some of the gotchas and implementation in Go, um, especially compared with one of the things actually I had in mind was comparing with how Python actually handle their arrays and slices, or what the different languages call their arrays and slices. Uh, anyway, let's just start with something just a very innocent looking two pieces of code, just to be able to uh, go through this one, have a rough idea in terms of at least how you mentally go through this one, and mentally think what is actually going to happen in each of these cases. Based on this, maybe we can get some of the uh, why certain things. Of course, once we actually explain why, it will be pretty obvious. Except that when you actually start programming a lot of these things, like for instance, okay, on the first main, we actually make an array. In this case, making an array of an int from 0 to 100. Okay, should this is actually a slice actually. So it means that this is actually a slice of length 100, sorry, a capability of one cap of 100. That means maximum of 100, and it's right now it's a size 0. So when you actually print a out, you don't actually see anything. So when you actually print a, you do not actually get a feel of the cap actually involved. It just, as it should, to be able to handle the high level stuff, it just prints okay, there's nothing there. It's an empty array, it's an empty slice in this case. So what we do in this case is that let's append it. In this case is that we if we append it with an array of int 1 2 3, what does it do is becomes that when you print a, you will get 1 2 3. Pretty obvious. Okay, so let's try a little bit different because of the syntax of how Go actually does things. Is that what happens when we actually append a, which we know is actually 1 2 and 3, with 4 5 6. So we assign the 4 5 and 6, 1 2 3 4 5 6 to a variable called c. Straightforward. Okay, so roughly a will be 1 2 3, c will be 1 2 3 4 5 6. Everyone knows that. So okay, let's try something. What if the first element of c is now negative 99? Okay, and then the first element of a is negative 10. Okay, what's a in this case, guys? Quiz. If you've not seen this before, what will be a be when this is actually printed out?
Definitely not negative.
Okay, so okay, definitely not negative 10. A is an array. So the first element of a is 1, negative 99, or negative 10. A was just assigned negative 10. So anyway, okay.
Because you made it like this, you made it obvious it's definitely not going to be negative 10. So definitely it's not normal.
Since you guys go no Go, so let's go through it. Okay, in other languages it's very pretty straightforward. So in this case, you know that okay, if you you know what, this as a sake of rather than running the pre this one, since it's actually interactive, slides are slides. Okay, let's do this live. Let's do it live. Okay, let's call this
Yes, I don't know go in the nitty, I mean the dirty little secrets.
that's when a lot of these nitty-gritty details actually comes out. Okay, so let's keep it simple. Print line A, C. Okay, let's just ignore this one first. Okay, oh, okay, wait. Okay, so this is actually called slices. Okay, so I'm not sure whether I can. Do I have a command integrate? Ooh, does it work? Yes. At least it's good for this slices. Okay, it's pretty obvious. A and C. A is actually 1 2 3. C is 1 2 3 4 5 6. Yeah, duh. Now let's say assign the first element of C to negative 99. Then the first element of is okay. Okay, what happened to negative 99? So in this case is that A is negative 10. You print A, of course, it's negative 10, 2, 3. Yeah, straightforward. But in this case, it also shows is that because of how the code slices actually work, it actually overwrites the C's, the first element of C. So you immediately get, you actually get 99. So if we do it like this,
it overrides. It's not because like it refers to the same thing.
correct, it refers to the same thing. Okay, I will show you all the all details later. So okay, now you know. Of course, it works like that because that's how Go works. Of course. So what happens if you do it like this? So okay, so let's revert this one first. Okay, this is 100. Of course it works like that. Of course it works like that. Of course it's negative 10. So negative 99 is no longer there. Of course it works like that. 0, 0. We just change the length of the allocated stuff in the beginning. It's pretty obvious, right? Okay. Answer is bam. This is when the gotcha actually happened. So this code over here is basically the ones at the bottom, the main two. So going through here, the difference between the original and the new is changing the size of the allocated slice in the beginning. So this is when the actual gotchas actually happen. So even though we know that sometimes slices in Go are references to an underlying array, so that we do not want to allocate way too many things, so that we actually have we refer the slices refer to the same physical memory to be able to save some memory. But because we are working with references, you must be very careful that anything that points and reference the same underlying array, they are going to have the same value. So same value over here, same value here. You change the same thing because A and C is referencing the same underlying array, you get the same value. Negative 99 is actually overridden. However, we have to remember another thing is that in Go slices, when we actually do all these things, appending and whatnot, is that the underlying array would be copied and expanded when there is actually not enough cap. When the size is actually not enough, it will be copied and allocated. So what happens over here is just that, okay, we assign this one, it's pretty obvious. When this line actually happens is that when we append 456 to A, because it's actually longer than the cap in a different underlying array is copied from A for 1, 2, 3, 4, 5, 6 with a different cap, then it's actually assigned to C. I'll go through this in details in another Go program. So that by the time these two actually happen, they are actually referring to two different copies of the data. Then you can get the gotchas.
But doesn't A get expanded already during the first one?
It does not. Because A here is that the way, this is also the problem with Go slices is that you can call append A with something else like this. It's not A dot append something. This is why unlike some other languages, we don't call A append 4, 5, 6. It's not. It's Python's syntax something like this. So it's actually not the append A something. This is not object oriented where it actually modifies itself. This is basically a function that takes the underlying slice over here, this one, to see whether or not we want to extend the original slice if it's actually expandable, or create a new copy of it, and this one.
How much the cap is supposed
Ah,
to scrape each time?
it's powers of 2. Okay, so okay, now that I actually went through the explanation, just to make things a lot more complicated to read over here, is that the same thing. I added a lot more code that is actually quite unreadable. But when we actually run this, so just going to skip through here, slices, they already explained this one, is that okay, let me go through here. Okay, so this particular not so readable Go code, what it actually does is that this is just a example when I actually run this particular Go program, is that rather than appending it, let's just say that 1 and 2 is actually assigned the integer 1, 2, 3. The 2 is actually 4, 5, 6. So when we actually print out over here, the code to do this is that print slice, we show the underlying structure of the slice, including the current length of the slice, the maximum capacity of the slice, the what do you call that, the pointer, the memory location of the slice, the underlying array of the slice, and then the actual how does the slice look like. So in this case is that okay, obviously this 1, 2, 3 is fixed size, the length is 3, the cap maximum size is 3, the actual data in terms of the memory location is this particular hex location, and within that particular hex location is 1, 2, and 3. And something additionally with a lot of those boilerplate codes is we try to use Go's runtime stats to roughly check and count. Of course, there's probably a better way to do this, but I'm just as a proof of concept, this, so we show this one. Number of actually memory allocations done by Go. So when we actually assign over here, where was it? Okay, so when we actually assign over here 1 and 2, of course there's no memory allocations done. Okay, so let's go to the first version of main one. This is when we have actually about 100 set. So about 100 set, when we run it, okay, let's make an array size 0 but maximum length of 100, assign it to A. Pretty straightforward. So how it looks like is A is actually of length 0. That's why we actually print out is blank, but you can store about 100 integers in it at this particular memory location. This is actually the one that's actually located. So this particular statement over here cost 1 memory allocation. Yeah, we know that, just straightforward. Yes, okay. So now when we try to append and reassign A to 1, which is 1 is this 1, 2, 3 over here, is then you will realize, you will see that A's length is now 3. Of course, is 1, 2, and 3. The cap is still 100 because we are looking at the original allocation is about 100. We are adding 3 to it. We are adding 3 elements to it. There's still plenty of space left, and then we assign it back to A. So you see from here, the underlying array structure, it is still at the same location, which also means that there's no allocation done. Pretty straightforward. So taking the same A, which of element 1, 2, 3 right now, we add the data from 2. So if you notice 2 over here, the location is not the same as this location. So even though also append A with 1, note again that we are not referencing the original 1. We are copying the data from 1, which is at this memory location 1, 2, 3, into the array of A. Plenty. A slice of A, sorry. And then same thing here, pretty straightforward, is 4 by 6, plenty of space. Now it's of length 6. Okay, no memory allocation. Of course, okay, when we actually assign this one, of course nothing happens, and then A, it becomes same memory location, of course it's negative. Straightforward. Now because we are normal programmers, in the beginning we do not know how big of size array we want. We are just working with array, and we are all used to JavaScript or Python or something like that, when we don't even want to think about how long can the array to be, because we are a lot high level, let's say in other languages. So we assign it to come on, 0, 0. Why do we need anything? This is actually important. You see from here, it does not incur any allocation at all, because in this case when we make a slice of integer of 0 length, of 0 cap, we don't need to allocate memory at all. And if you notice this particular really quite small number over here, in terms of the what they call that, the memory location is actually quite low location. It's probably in Go, I'm not sure, I'm just saying this, something that's already pre-located with you can reuse and point to the same empty set over here, empty array over here, empty. No big surprises. But when we start adding the contents of 1, which is 1, 2, and 3, we realize that A over here originally cannot fit that particular data. So in this case is that there is actually a new array created of cap. We didn't even say how big it is. We know over here 1 is actually the length is 3. So the length is actually 3. Because using powers of 2, a new array location of size, maximum size cap of 4 is actually allocated and assigned 1, 2, 3. So if we add another element to this one, 4 for instance, we will not incur another memory allocation. Straightforward. But the biggest difference you see from the original and the new one is that if we never use A at all, we save ourselves one location, so that when we actually assign value to it, when we want to append to it, this is when we know what size we want to use and we allocate just enough for this. So this is when we actually allocate the memory. However, it also means is that the memory we used up is only 4 bytes instead of the original, in this case is that 100 bytes. So it's better, more efficient. Yes. But going on, okay, now we can add another array to this, 4, 5, 6. We can add 4, but then 5 and 6 is way bigger than the cap of 4. So what in this case, if you notice from this particular memory allocation is that there is a new array allocated, and then the original A from here, 1, 2, 3, is copied into this new one, incurring a memory copy. Then the 4, 5, 6 is actually entered there. Another memory allocation that's actually being done. So in this case, and then this new memory allocation is assigned not to A but to C. If it's actually assigned to A, what happens is that the original 1, 2, 3 array can be garbage collected and reused for other things. So in this case, if it's actually assigned to C, A, the original data of 1, 2, 3 remains at a different location. So what happens? Okay, again, this thing happened. First element of C, negative 99. First element of A, negative 10. But because we did two different allocations over here, these two are referring to two different memory locations. And what you get is that, oh, okay, A is actually negative 10, 2, 3. C is negative 99, 2, 3, 4, 5, 6. Without any memory locations, of course. So yeah, just one line of things actually cause a lot of different gotchas over here. If you try something very similar in Python, because I think Python and other languages, you don't really specify there's no such thing as a cap, you don't specify this. Whenever you do an array append or array slice copy or reference to a slice, you actually do a copy of the data, a shallow copy of the data. In Go, when you do a slice, you are referring to a subset of the original slice. When you try to append to it, that particular slice will be copied, then will be copied. Before that, referring to the same slice, no data is copied. So in this case is that if you are doing some read-only operations when you are comparing this and this one, slices, the way that Go works is a lot more memory efficient. The gotcha here is just that if you ever modify any of your slices, the mental hurdle, bookmark, or whatever you call it, you have in mind when working Go slices, that whenever you need to make modifications to your slices, you have to be careful that you don't get these gotchas. You don't have this problem in Python. That's why some of my original hack code in Python works perfectly, and then when I ported directly to Go, it doesn't work because I was doing some slice modification. Yeah, so that's the gist of it. In Python, it just very boring, looks like this. So Python, oh okay, another Python, okay, Python. Let's try something similar in Python.
When you assume that when you do that kind of assignment, you think that you are doing a reference, so you think, oh, it happened when you try to be too smart.
I'm not sure about Python that much. Is this correct?
Yeah.
Is this a similar code?
Let's try it out. Oh, you broke our traffic cap.
Ah, just ignore it. slices
Where's the camera?
inside the box. How do you append in Python again? I'm not. Is it like that?
Yeah.
No, it's
No, start. Give it a start. Give it a start so it will be where I think in front of the list.
what?
The start. So the start.
Oh, okay.
It's not like this. It's start. Start then the list. Yeah.
Does it work?
Yeah, then it will be a list. Yeah, so grab it as a list.
Yeah, like that. Just
Star and a list. Star of a list. Yeah.
so what I do wrong?
Yeah, you don't need this. You don't need the red. This one here.
Like that.
No, you need the star, but you don't need this extra bracket. You had an extra bracket.
Like that.
No.
Tough.
No, it's has to be a list.
So what's the difference between the line number 4 and number 2 then?
You add a list as an item, but this one you unpack it. I'm not sure if it works. It doesn't work.
Doesn't work.
So it has to be one to one. Exactly one.
You guys.
I think it's the extent.
Obviously we suck at Python. See, no, unpack.
Extend. Extend. If you want to extend, it's not append, it's extend. Then you put a list here. Then it's normal list. A list. You have to be a list.
How do you do a list in Python? This one.
Yeah, the same or this lah. This is a list lah. But that is the or they remove that.
I don't know.
Used to be valid syntax.
Yeah.
Okay, then it should be good. Yeah, should done.
Okay. It's pretty, okay, so A number 0 is equals to -10. C 0 is, of course, because wait, this is not what I expect. Wait,
I think it's just a reference. It's not even a copy.
no, I was wrong. So C is supposed to be, this is a reference.
Yeah.
It's a gotcha. Okay. So this, if C equals to A, that means that C and A refers to the same list. So if C equals to A like that, means is that it copies the contents of A.
Shallow copy.
So this is a shallow copy.
So if you change A to contain a list item, then
so the other test I did just now was like that. Oh no.
shallow copy.
What, different like?
Another bracket.
Did I miss a bracket? Yep. No.
Follow the rainbow.
Okay. So what it means is that over here is number 0 to number 0 2. The 0 equals to -10. What do we get?
Shallow copy.
It's a shallow copy. I think it'll be really confusing to beginners, I think. Yeah. Do you guys actually see the gotchas? Yeah, so the slice is actually a shallow copy. So if you do like this, is a reference.
If your A equal B, will be taking a whole reference. But because of that, by position, you do a copy.
Yep. The difference is that in Go, the equivalent of doing something like this.
Yeah, because it's shallow.
The Go problem is that this in Go is not a copy. It's actually a reference to the same. It's still a reference to the same underlying array. That one's the one that caught the gotchas.
Capacity is
Yep.
zero until the last element, right? In Go.
In Go,
Go when it grows, it becomes another person.
okay, so let's do the other. Okay, let's say our original example here. Right? Okay, screw it. Okay, let's try the.
Why your code is so lag? Your VS Code is so lag.
It's slower CPU. It's quite fast here. It's slower there.
Oh, okay.
So it's a CPU. I need to upgrade to the latest i9. Shut up. Yeah, ridiculous. I can buy a car with that. Let's try something like just now. It's in 1, 2, 3. Okay. So C equals to A. C equals to A. Okay. A0. Okay. 1, 2.
It's a 12-inch.
C mouse case.
Points to the position. The casual MacBook.
Yep. So in this case.
The old MacBook before the current MacBook, right? The plastic instead of the magnetic, right? I don't know what's the point. The super thin one. Oh, yep. the MacBook.
So in Python, this will be a copy of it. So that means is that C will be separate from A. But if we do, let's say A1 equals to dash negative 99, we will actually see that C's will be negative 99. Yep. Okay, so the gotcha is also over here. When we do something like this in Go, both C and A will be referring to the same array. In Python, when you do something like a slice like that, you can actually expect that especially if everyone is working with a flat list of integers. In Python, something that on line 7 like this, it is actually a copy. In Go, it is actually the same reference. Gotcha. Okay.
So is there any like Golang or Golang where they will warn you about all this?
Just like an initiated map, it still doesn't warn you, right? If you do a var m equal map something, right?
I know.
And then you initiate it, it
I know.
still crash, right?
I know.
If you read it, it's fine. Yeah. If you try to allocate,
This one is gotcha in the sense that this is not an error. It's a feature. It's just that the programmers will misunderstand, and if you try to assign A like that, it is actually modifying both A and C at the same time. It will affect A and C at the same time. This particular time.
But you all used to write C, right?
Let's put it this way: when we write C, we never had this type of problems because we suck at C. At least I suck at C.
No, also because everything is pretty fixed. Last time when you learn, but allocation is fixed. But if you wrote C last time, then you feel like you have precaution when you do this kind of.
When we do C, when we do a lot of array manipulation, I remember last time was that I malloc something huge and then I printf to that one. What essentially means is yes.
Yeah, but if you've done C before, then you would be.
In C, how I avoid this problem is that I do a copy all the time, so I don't have the referencing problem. At least, yes. So if you want doing a lot of referencing to this one and doing a lot of array manipulation, the way I used to avoid a lot of these shenanigans and this one is that I malloc all the time and I forgot to feed them all the time and I memory leak all the time. So tracking down the memory leaks last time was a lot more fun. Oh yeah, you have a tool for that, but you still need a tool for that. So it's actually last time also in C is just that how you guys actually do. Oh, let's say you want to do a printf something like that, right? You will need to make sure that when you printf, either you print to the standard out, or if you printf to a string, you must tell the C library how long is your maximum string, the length, or else you get array of chars. Okay, pointer to chars. Ha 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 ha. Pun pun. Sorry. Never mind.
Oh, I know where.
There's some lot. No. Okay. So anyway, that's the gotcha for Go. So if you're using a lot of slices in Go and read only, it will save you a lot of memory. Unlike C, where you lick it all the time. At least I do. So the gotcha is just that you cannot use Go slices like Python slices. So whenever you guys say slices or arrays or lists or something like that, I think we mentally have to remember what languages we are dealing with, because not all of them are exactly the same. I actually got the gotchas. So the other gotcha is just that Chiliong over here, still originally until 1 hour ago, think that Python list is a linked list. Python lists are implemented as arrays, exactly like Go. Proof. So okay, variable length arrays. Python lists are variable length arrays, exactly like Go, not list style linked list. Okay, implementation use a quantitative reference to keep pointer to an array and the array's length. Okay. When the array must be grown, extra space is allocated so that next few times don't require an actual resize, exactly like Go, except that when you reference like a slice like that, it does a copy, not a reference, unlike Go. That's when the gotchas happen. All right. Okay. For those who still do Go at Python.
They lie. They call it a list. What do you call it?
Today I learned in Go a lot of Python stuff.
What do you call it? A list man is an array.
Dictionaries are maps. Dictionaries are hash tables. Okay, easier to remember. Hash tables.
PHP array is more fun. It's also a hash table.
Oh my goodness.
It's also a hash table.
I swear that's why the PHP guys, when they go to Python or Java or Go, they actually has the mental arrays and stuff.
Are you guys gonna show it?
I'm done, by the way. I'm just going to randomly go through things.